Hi, I'm Yi. Today I'm going to introduce the chain rule for vector values theorem. Well, I will introduce the chain rule first, then go through the vector values theorem of chain rule, then I'll give you the proof. So what is the chain rule? If O and U are both open set of real numbers, and the function f is from UO to R and G is from U to R. They are continuously differentiable with FO contained in U. So then the composite function g of x from O to R is also continuously differentiable. And moreover, for a point x in O, the derivative of g of x is equal to the derivative of g of fx times the derivative of fx itself. So what is the chain rule for vector value theorem function? So let the O be an open set of subset Rn, and suppose that the mapping f from O to Rn is continuously differentiable. Suppose that also the U is an open set of Rn, and the function from G from U to R is continuously differentiable. Finally, suppose that the FO is contained in U, then the composition G of F to R is also continuously differentiable. It's like the definition of chain. So moreover, for each point x in O and each index I, which is ranged from it is greater than equal to 1 and but less than equal to n. So we have the chain for vector value function like function 3, which is the partial derivative of g big fx is equal to the sum of dj derivative from j to n g fx times the partial derivative of fx over xi, partial derivative of xi. So that is the gradient of g of x fx equals to the g gradient of g fx times the derivative of fx. So we can see that the equation 4 is the matrix form of the equation 3. So let's go to the proof. So let x be a point in O since the O is open. So we can select the positive number R such that for the open ball x, BRX is contained in O. Moreover, since the mapping F from 0 to O to Rn is continuous and U is R, open set of Rn. We can also suppose that the segment joining the points fx and fx plus h lies in the U if the absolute value h is less than the positive number we chose, which is R. So for the each h in Rn such that the absolute value of h is less than R, we define the RH is equals to the fx plus h minus the fx minus the bfx times h. So according to the first order approximation theorem for mappings, we have the limit from h goes to 0 of the absolute value of h over the absolute value of h is equals to 0. So by the definition of RH, we given both. We move the BF from right hand side to the left hand side, then it becomes the RH plus DF x times H is equals to the FF plus H minus the FX. So now for each H in Rn, such that the absolute value of H is less than R, we can apply the mean value theorem to the function G, which is from U to R on the segment joining the point fx and fx plus h in order to select a point on this segment. So we choose the label which is VH. So we have the equation becomes the g of f of x plus h minus g of x equals to the inner product gradient of g of v of h and f plus x plus h plus the fx by substituting the equation 8, we have the g of x plus h minus the g of xx is equal to the gradient of g of v of h b f x times h plus the gradient of the inner product of the gradient gv h and rh. So by observe the continuity of x, which is from O to Rn, it implies that the limit from h to 0 of v of h is equal to the fx. So we fix an index I, where I is less than the n but greater than the 1. So for number t that from the which is range is its absolute value is less than the r but greater than the 0. If we define that h equals to the t times ei, then from the equation 10 we obtain the g of x. We change the h to t. We have the g of x times g of x plus t minus the g of x of f of x over t is equal to the gradient of g of v of t and df xei plus the inner product of the gradient of g of v of t and the r dei over t. So for this equality, by using the 7 and 11 equation, which is this one, the definition of h, and by changing the h to TEI, the function 11, we have the partial derivative of g of x, f of x, and over partial derivative of xi is equals to the inner product of gradient of g of x and the dfei. So, but it's still different to the original equation. So, but the df xei here is equals to the sum of the formula of f partial f x or x over xi from f1 to fn. So the scalar equation from 14 we given is exactly the equation of 4, which is this one. So we finish the proof.